Hello, welcome to this presentation on identifying linear functions by tables. You can sometimes identify a linear function by looking at a table or list of ordered pairs. In a linear function, a constant change in your x corresponds to a constant change in your y value. So let's look at some examples to figure out what I mean when I say you can sometimes identify a linear function by looking at a table or a list of ordered pairs. In a linear function, a constant change in x corresponds to a constant change in y. So what I mean here is, let's look over here. From 0 to 1, that's a difference of 1, right? From 1 to 2, that's a distance of 1. From 2 to 3, that's a distance of 1, right? So each of my 0, 1s, 2s, and 3s, they're the same distance. So I'm going to put a little check. That checks out. So this could be a linear function. So when we go one space over here, we go 3 over here. When we go one space with the x again, we go 3 more on the y. And then we go, once again, when we go one space from 2 to 3, we're going 3 more. So 3, 3, and 3, right? These are all the same number. So that checks out. So this is a linear function. So when you have a table and your rate of change over here is the same, in this case it's 1. So when we go one space, we always go 3 spaces over here, right? What if we went 2 spaces over here? What if our next one would have been a 5? Well, then this would have had to been, so if we went 2 spaces to 5, we would have had to go 6 spaces, so that would have been an 18, right? Does that kind of make sense? Try to think about that for a minute. Okay, so now from 0 to 2, that's 2 spots, right? 2 to 4, that's 2. 4 to 5, that's 1. So let's figure out if this is linear. If we go 2 spaces from 0 to 2, that's a 2. Not a very good 2, but trust me, that's a 2. We go 2 spots over here. When we go from 2 to 4, which is 2 spaces, we go 2 spaces. Then we go from 4 to 5 over here, which is how many spaces? Just 1 space, right? So if we go 1 space over here, how many spaces should we go over here? We should go just 1. For it to be a linear function. So since that works out for us, this is linear, because we got a constant rate of change. That just means constant rate of change. So let's think about this. So we went from 0 to 2, that's 2 spaces, right? So we went 2 spaces, and we happen to go 2 spaces over here. 2 to 4 is 2 spaces, 4 to 1 is 1 space. So kind of think about in terms of how many spaces you're going on your number line, your graph, or whatever. They've got to be constant. So since they all worked out evenly here, that's a linear function, even though it looks slightly different. This one you're going to have to think about. Maybe graph it, play around with some of the numbers. That's what you're going to have to do to make full sense of it. Here, we go from, we're going 2 spaces, we're going 1, we're going 1, right? Here we've gone 1 space, 2 space, 2 space, right? Well, let's see. So if we go 2 spaces, we've gone 1 space over here, which means, if we went half the distance, we should have only actually went a half a space, right? For this to be linear. So this is not linear. Not linear. Let's look at here. We go 2 spaces, 1 space, 1 space, right? Here we go 0 spaces. I mean, these are all the same numbers, so that's constant on this side. Not constant over here. So it is not linear. So it's not linear, right? Because, every time because, when we went 2 spaces over here, we should have had some sort of different number here, right? When we went 1 space, that's okay not to have any change. So that's a linear function. And if you were to graph this, if you were to graph that, it would be a function of that. So, next one. So you're going 2, 1, 2, but the thing I notice here is I got 2 2's, right? This 2's paired with the 1, this 2's paired with the 4, so this is not a function. So if you see that, don't go any further. It's not a function. Last one here, we're going a distance of 2, 1, 1. Here we got a distance of 1, and each time we've got a... So we're constant here. Not constant. It's got to be constant on both sides in order for it to be a linear function. So this is not linear. So it's a function, it's just not linear. Let's look at one more example. And you can get this worksheet off the website. If you're on YouTube, just click on that link. There's like 4 practice problems with the answers. And it's because we're running out of time. I'm not gonna do all of them. But here you've got a distance of 1. On this side you got a distance of 4,000 over here. So that's linear because it's constant. Here's a, and I give this on test a lot. Students miss this, pretty regularly. 0 to 1 is 1, right? From 1 to 3 is 2. 3 to 5 is 2. 5 to 10, that's 5. 10 to 10 is 10. 20 to 30 is 10. So here's what you got to watch out for, guys. If you're going 2, for 2 spaces here, you're picking up 10 on your distance. 2 spaces here, you're picking up 10 on your distance. 10 divided by 2 is 5. So that means each unit of time is going to give you 5 more miles, right? So if you wanted, sometimes people do this, and I've got no problem with it. They'll put in a 2 here, and they have a 15. Put in a 4 here, and they have a 25. And then that makes it a little bit clearer to see it from the table, right? But what you got to realize is it's still constant, because if when you go 2 distant, each time here we've gone 2, we've gone 10, right? If we if we had a 6 here, this would be a 35. So it's a constant rate of change because our average rate of change, our average time, distance, it's always going to be the same. So good luck with this. I hope this helps you out a little. If not, stop by the class, ask questions. If you're on YouTube, send me a message, and I'll try to help you out the best I can.